Hello, in this video, we are going to be talking about the solid phase of matter and incorporating what we know about molecules into our discussion of the solid phase of matter. So just a reminder, the solid phase is the phase in which a substance's particles are fixed in close proximity. We now know that there are different kinds of particles that create solid phases. When we have ions put together into an alternating pattern, they stick to each other in close proximity. That's an ionic solid, and a solid made of an ionic compound. But we can also talk about atoms that have been arranged in a fixed pattern, as well as molecules, where molecules have actual bonds connecting atoms together to make a pattern in the solid phase. What actually makes molecular and atomic solids different from ionic solids? That's what we'll investigate. So to take a closer look, let's say, for example, table sugar. So when table sugar becomes a solid, we can see it actually forms very organized geometries. And if we zoom in on the molecules of the sugar in the solid phase, what we see is that even though their sort of single particles are represented by a Lewis structure connected by chemical bonds, there's an alternating pattern of how these molecules stack together. So we call these molecular solids because they're made of molecules rather than ions. And they're close enough together that they retain the solid organized phase that we can see on a larger scale as crystalline. But the biggest difference between this kind of solid and ionic compound solids is that what are molecules held together by? In other words, how is this single sugar molecule sticking to this other single sugar molecule? Is it going to be an ionic bond? Is it going to be a covalent bond? It's going to be intermolecular forces. Remember, intermolecular forces are the types of forces that stick molecules together. They're weaker than actual bonds, but they include the dispersion force, the dipole-dipole force, and hydrogen bonding force. So that's the biggest difference between an ionic solid and a molecular solid. The molecular solid, the molecules stick to one another through a weaker kind of force. And for this reason, we expect and we observe in real life that sugar melts at a lower temperature than salt. In fact, it melts so at such a low temperature that it can burn very easily. But one thing we can do is try to predict why sugar molecules make crystals as well. And why do molecular compounds make crystals in most cases as well? Well, here is an example of a sugar molecule. What I have here is highlighted some specific atoms. What I'd like to do is sort of just zoom in on each one of them and their connectivity in more detail and identify what the geometries of the labeled atoms are. So what I'm going to do is I'm going to redraw this, because what's happened is that this is drawn in a way that we're not showing every single atom. Otherwise, it would be very cluttered. So I'm going to redraw them showing the atoms of the highlighted regions. What I'd like us to do is determine the geometries. So here we have the highlighted region sort of enlarged a little bit. So the question is, what geometry do we have at this carbon? So this has a carbon with 4 bonds, 4 groups. So this is going to be a tetrahedral. I've zoomed in on an oxygen in part of this sugar molecule. There are 2 bonds to it, and what's not shown are the lone pairs. Here they are. So what molecular geometry does this have? Oops, sorry. This is bent. And then finally, this carbon that's highlighted here, I've emphasized the actual bonds that are connected to this carbon. So what is the geometry at this carbon? This is also tetrahedral. The point is that when we zoom in on these pieces of molecular solids, we expect there to be very distinct geometry based off of VSEPR, this idea of electron groups spreading apart from each other. So it should feel comfortable that there's a similarity to ionic compounds. They make very organized crystalline solids because at each position we have very specific geometries. Tetrahedral with its specific angles, bent with, again, very specific geometries. What we're getting at is that molecular solids are like ionic solids. They can be crystalline and share that sort of particle picture. But the difference, the major difference, is that we expect, actually, I can't go back to this. We expect that the properties of an ionic solid are different than a molecular solid because the ionic solid is held together through non-directional ionic bonds, right? It's bonded in all places simply by the fact that positives are attracting negatives from all surroundings. Whereas molecules, they have very specific connections, and individual molecules are only attracted to each other through intermolecular forces, which are much weaker. So we expect molecular solids to have lower melting points than ionic solids. And the case will be even more extreme for atoms. If atoms are together, again, that means there are no bonds. It's just single atoms in a solid. Again, they'll be attracted to each other through intermolecular forces. Which intermolecular force would be the attractive force of atoms, just individual atoms? Well, is an atom polar? Well, to be polar, you have to be sharing electrons. Atoms are just single atoms. They're not polar. So that means by default, they're nonpolar. So what force of attraction do atoms have with each other? They have to be nonpolar, so therefore dispersion force. So that's the big difference between molecular and ionic. They can both be crystalline. However, the actual particles picture is very different. Ionic compounds have ions alternating, positive, negative, whereas molecular solids, you see distinct, obvious molecules that are stuck to each other, but they themselves are also organized. Because they're stuck to each other by intermolecular forces, molecular solids have lower melting points because their forces of stickiness are weaker than ionic solids, which have ionic bonds.